Let us consider this problem. We have a plate with a frictionless surface which is oriented at a certain angle to an incipient water jet. So this is the plate and this is the water jet. And the velocity is uniform over each cross section. So the water jet goes, hits the plate and gets deflected like this because of the orientation of the plate, and it is given that the velocity is uniform and the flow is inviscid and incompressible. The angle made by the plate, the vertical angle is theta. So the question is, we have to express, we have to find out an expression for the force. Okay, it is given that this is A naught Q naught, this is A1 Q1, and this is A2 Q2. So first things first, the control volume, let us choose the control volume as shown. So at level 0 fluid enters, at level 1 fluid exits, at level 2 also fluid exits. So conservation of mass, let us write down. So ddt of integral rho dv plus integral rho u minus b dot n dA equal to 0. So now for the control volume is stationary and it is not deforming, the flow is steady, so this is 0. So essentially this boils down to integral rho u dot n dA is equal to 0. So at section 1, u dot n, u is in this direction and n is in this direction. So n is like this, u is like this. So u dot n dA is equal to minus of q naught. So this becomes rho times minus of q naught. What about section 1? It becomes rho q1, and at section 2 it becomes rho q2, because at section 1 integral rho u dot n dA will be equal to integral rho u. So because it's constant, the velocity is uniform across a cross section, it will be u1 times a1, because u dot n will be positive. U dot n cap is simply u, unlike here, and u times a1 is the volume flux, so this becomes rho times q1. So this is why I've written this directly, and you can take your time to just figure out how this comes into picture. So this will be equal to 0. So this gives us a relationship between the various q's, and so we have q1 plus q2 is equal to q naught, and q1, I mean essentially it is a1 v1 plus a2 v2 is equal to a naught v naught, because q is equal to area of cross section times the uniform velocity. The velocity is uniform and hence we can write this. We can disregard the integral, no problem. Now let us write down the momentum conservation equation. So the momentum conservation equation, let us write it down in this stream direction, and let us define the normal to it also, it doesn't matter. So we want to balance the momentum in the stream direction so that we can get a thrust on the plate. So this is the plate. We are more interested in the momentum equation in the n and in the s direction. So let us write it down in terms of the vector equation. Okay. So ddt of integral rho u dv plus rho u minus b dot n dA is equal to the forces. So let us decompose the force as force acting along s direction and force acting along the n direction. So these are the forces acting on the control volume, that is on the fluid due to the solid plate. So this particular term will vanish because everything is steady and the control volume is not deforming. What about this? It will be rho u dot n dA. So now let us write this down into the control volume. So what is coming in? So let us decompose it into the first. So cross section 0. What is this integral going to be? It's going to be, so now this u velocity we can split. So this is essentially this direction and this angle is theta. Okay. So this angle is 90 minus theta. So u, the inlet velocity, we can split as u naught sine theta es minus u naught cos theta en, because this velocity component will have this projection in es direction and this projection in the en direction, and this angle is theta. So u naught cos theta is minus n direction, this and this. Okay, while u dot n cap is still going to be simply minus u naught times dA. So u dot n cap, because u is into the control volume and n is out of the control volume, we get this minus sign. So this becomes integral rho u naught sine theta es minus u naught cos theta en, and this integral we can take away because the velocity is uniform across the cross section. So this minus sign, we write it over here, this becomes u0 a0. What about this particular term for section 1? It will be integral rho, and this velocity is u1 in the es direction times the flux, so it will be simply u1 times a, and this integral vanishes because I have directly written down all the integrated stuff. What about section 2? It will be rho u2. Now the velocity is in the minus es direction, so this will be minus rho u2 es, and the flux will be u2 a2. So this entire term we can write it down as rho u1. Okay, so let me write this down as q1. This is in the es direction. This is going to be minus rho u2 q2 in the es direction. This is going to be minus, so this is q naught, so minus rho q naught u naught sine theta in the es direction plus rho q naught u naught cos theta in the en direction, and this is going to be equal to fs es plus fn en. So this implies the f in the s direction is going to be, let us collect all the terms in the s and n directions respectively. So it's going to be rho u1 q1 minus rho u2 q2 minus rho q naught u naught sine theta. The force in the n direction, it will be equal to, so in the n direction it's going to be simply rho q naught u naught cos theta. So now in due course we will make use of additional constraints arising out of the Bernoulli equation, but not right now. The important thing is to understand how we can decompose the fluxes into some other convenient direction. Based on that, we can write down the momentum equation. So this is the momentum equation in the vector form. I have not split all the components. This is going to be the momentum vector carried by the flux, and this is going to be the flux. So this is actually a scalar. This entire thing is always going to be a scalar, as we have seen, but this thing is going to be a vector. Okay. Let us consider a problem in which we have a tap or a pipe bend. All right, this is a pipe, and fluid comes in at these conditions. So rho 1, A1, V1, and it exits at not rho 1. This is the density is constant. This will be P1, A1, V1, and it exits at P2, A2, V2. So it enters at a certain pressure and it exits at a certain different pressure. So it is given that the weight of the elbow is equal to W. The question is, what is the force required to hold the elbow in place? Okay, so there will be some force required to hold the elbow in place. So first of all, let us draw a small bracket. So this bracket is holding the elbow in place. So now force because of the bracket on the elbow, right? This will be because of the weight of the bracket plus force due to water on the bracket. So because of this bend, you can imagine the pipe will try to move like this, right? But we have to quantify that. So the force because of the bracket on the elbow will be equal to the weight of the bracket plus the force acting because of the water on the elbow. Sorry, this should be elbow. So this is the force of the water on the elbow. So let us find out the force on of the elbow on the water. Force elbow water, we will draw a control volume like this. Essentially it is this control volume. So whatever forces this control volume has, so whatever force, that will be force on the force on the so this is the force on the water because of the elbow. Alright. So just to recap, force on the bracket because of the elbow is equal to the weight of the elbow plus force of the water on the elbow. So we are to find out what is the force on the elbow due to the water. Let us consider the water to be, so let us denote it by W. Let us denote the elbow by E and the bracket as B. So force acting on the bracket will be due to the weight of the elbow plus the force acting on the elbow because of the water. So but first we can find out what is the force on the water because of the elbow. So let us take this particular control volume. So for that one control volume, what do we have? Alright. So before going into that, let me just draw it separately. So this is P1, A1, V1, this is P2, A2, V2. Alright. So now, okay, let us first write down the conservation of momentum. So ddt of integral rho u dv plus integral rho u dot n dA equal to the force on the control volume. So the point is, this is a steady flow and the control volume is stationary. Okay, the control volume is not deforming. So this time dependent term will vanish. So then we have integral rho u dot n dA is equal to the force acting on the control volume. Now at the left end, what is rho u? It's going to be rho v1. Let's draw this as the x direction and this as the y direction. So rho v1 ex, this is the for this particular term, and what is u dot n dA? It's gonna be, so u dot n, so velocity is in this direction, n is in this direction, so u dot n will be minus v1 times a1, and we have assumed that the velocity across the cross section is uniform. So we have assumed this, no problem. Plus, what is the flux coming out? It will be rho v2 minus ey in the minus ey direction, and the velocity is in this direction and the normal vector is also in this direction. So this will be minus v2 a2, and this will be all the forces acting on the control volume. So the left hand side, essentially, what does it become? It will be rho a2 v2 square ey minus rho a1 v1 square ex, and this will be equal to the forces. Now, what are the forces going to be? Okay, so the forces are going to be because of a difference in the pressure also. Right, the pressure over here is P1, the pressure over here is P2. So if you have, so we know from hydrostatics that if you have an object, pressure over here is P1, pressure over here is P2. So the net force will be the difference in pressure times the area. So that has to be also accounted for. Okay, so we can write, okay, before writing any expression, let us look at something interesting. If I draw an imaginary control volume like this, right, and if I subject the entire control volume to atmospheric pressure, and it is actually subjected to atmospheric pressure, all the forces on this white control volume will vanish, because from all the sides it is acted upon by atmospheric pressure. Now, having said that, what is then the effective pressure at this point? If you superpose this, at this point the effective pressure will be P1 minus P atmosphere, and at this point it will be P2 minus P atmosphere. Notice that I have put the direction of the pressure as compressive. Okay, it's compressive. Pressure is by default always compressive. So then essentially this is the gauge pressure. So this is also equal to the gauge pressure, and this is also equal to the gauge pressure at point 2. So the force in the x direction will be equal to P1 gauge times the area of cross section 1, because see, whatever the influence of atmosphere is, this area, if you say that there is some atmospheric pressure also pushing it in this direction, you can take the same area over here and that is pushing it in the other direction. Okay, so it's like you draw an imaginary control volume where you have atmospheric pressure acting uniformly, then you simply subtract that base pressure. Pressure, as we know, is always is always having an offset. So this is the ramification of that idea that pressure is never absolute, but it is sort of dependent on the differences between pressures. And so the base pressure here is the atmospheric pressure. Okay. So at both the ends, it's almost like the gauge pressure is acting. So the force in the x direction is P1 gauge times the area, and this is EX direction, plus P2 gauge A2. So let me just put this subscript slightly smaller here, times A2 in the Y direction, plus now what else will the control volume have? The control volume will also have some mass of fluid also residing in the control volume, plus the volume of the volume of this bend times density of water times G, and this is acting in the minus EY direction. So these are plus the force. So these are the fluxes. These are the forces due to pressure. This is the force due to the weight of the water, and there will be an additional force acting on the water because of the elbow. So then, with the help of this, we can write force water on the elbow, water because of the elbow, not the on the elbow. So force on the water because of the elbow will be equal to rho A2 V2 square EY minus rho A1 V1 square EX minus P1 gauge A1 EX minus P2 gauge A2 EY plus rho water G volume of water EY. So this will be the force acting on water because of the elbow. So then minus of this, minus of force, this will be force on the elbow because of the water. So once you know the force acting on the elbow, in order to restrain the entire object, so force of, so let me just modify this. So force acting on the elbow because of the bracket plus the weight of the elbow plus force on the elbow because of the water, this whole thing has to be 0, because the elbow is in static equilibrium. And this is, if this is true, this will give us an expression for the force acting on the elbow because of the bracket, and the minus of that will be the force acting on the bracket. So this is how you can design a bracket. Okay, let us consider another problem in which it's a very conceptual problem. We have a stream tube, that is the collection of streamlines, which looks something like this. So using this central streamline, so this direction will be the streamwise coordinate, and this distance is ds. The angle this streamline makes, let us call it theta, where gravity acts in this direction. So the question is, what is the, can you show that across the streamline P by rho plus half u square plus gz equal to constant? That is essentially using the momentum equation. We want to prove the Bernoulli equation. At least the Bernoulli equation in its reduced form. So let us first write down the conservation of, so let us draw the control volume. This is the control volume. It encompasses these two flat ends and the shape. The control volume has zero velocity, it's a fixed control volume. Alright. The control volume is not deforming. So we can write down conservation of mass as follows. So ddt of integral rho dv plus integral rho u minus b dot n equal dA equal to 0, and because of the velocity being 0 and the control volume not deforming and the flow being steady, we can write down integral rho u dot n dA is equal to 0. So this is the statement of the conservation of mass. What about conservation of momentum? I'm not writing down the unsteady term. So it will be directly rho u dot n dA, and this will be equal to the forces acting on the control volume. So the forces acting on the control volume will be due to the weight of the fluid. So it will be integral rho g dV, and it will be because of the pressure. So if I write down the expression for pressure, so the force due to pressure will be minus P, and so if I have a surface and I want to find out the force due to pressure, I know that the force is sort of compressive. So in that case, I can write down the force acting on this surface as P dA, but there will be a minus sign, and the direction of the pressure is along n. So this minus n vector is indicating that the force because of the pressure, which is PdA, is compressive in nature. So this will be P n vector dA, where n vector is the normal to the area. Let us first, or yeah, let us write down what we obtain from the left hand side, or let us first write down the conservation of mass. So conservation of mass. So because these are the streamlines, there is no mass crossing the streamline. Okay, streamline by definition, there is no mass crossing. So there is no flux through these side walls. The only flux that is coming in is because of this face and this face. So what is the flux coming in through the left face? It will be integral rho velocity at this point, which is u times dA. But what is u dot n cap? So u dot n cap is going to be negative because n cap over here is pointing opposite to the direction of the velocity. So there will be a negative sign. And this will be, if we assume that over this face, I mean, it's not an assumption. If we take a very small element, it's going to be true. So we will have rho, so this will be equal to minus rho u times A at this point. So this is at the left face. What about the right face? At the right face, integral rho u dot n cap will be integral rho u at s plus u at whatever this location is plus delta s. So it will be u at this point plus del u del s times delta s. So we're making use of the Taylor series. So I can write it as ds, no problem. So this is the velocity at this point written in terms of the velocity at this point, right? Times dA. Now the area is also changing. So this can be written as rho u plus del u del s ds times the area at that point. So we are again assuming that until we hit the next streamline, we have a constant velocity, and this will be a plus del a del s ds. We can similarly write the a at, so this is essentially a at s plus ds, and we don't need to write down the explicit formula for the area because this stream tube need not be even a circle. So we write it in this form. So if we combine this and this, the statement of conservation of mass becomes rho u plus del u del s ds times a plus del a del s ds minus rho u a is equal to 0. So that's the statement of the conservation of mass. Let us copy the statement so that we can work with it on the next page. Let me just copy the schematic as well. So let me rub out the non-important part. Alright, so now let us write down the statement of the conservation of momentum. So what about the left hand side term? On the left face, you are we can write the momentum in the ES direction. So actually everything will boil down simply to the S momentum equation, because in the n direction there are no fluxes, so there's not going to be a force, at least in this case. So as fluid transits across point on the left to the point on the right, distance ds, we can write down for that small short segment the conservation of momentum as follows. So incoming, the momentum is rho u, and u dot n cap is minus u times dA. So this is for the left face. So this will be rho, so this will be minus rho u square times A. What about the flux through the right face? It will be rho u plus del u del s ds. This is the momentum flux coming out, times u dot n cap. So it will be simply u plus del u del s ds times A plus times dA, and essentially because we are assuming it to be constant across the cross section, this particular term will become rho u plus del u del s ds whole square times A plus del u del s ds. But from the conservation of mass, we already know that rho u a is equal to rho u plus del u del s ds times A plus del u del a del s del a del s ds. All right, and this we can write down as rho u plus del u del s ds times, so there will be one u plus del u del s ds plus, times one term which will be A plus del a del s ds. So from the conservation of mass, we can write it as ua. So these are the two fluxes. So at least on the left hand side we have rho u times u plus del u del s ds times A minus rho u square A, this term. Now what about the terms on the right hand side? So this will be equal to the force due to the weight of the fluid plus force because of the difference in pressure. Yeah, and difference in pressure will be because of two things. The first will be the fact that the control volume area is increasing, right? If the control volume area is increasing from one end to the other end, and the pressure is also changing, that will give rise to a force in this direction. But this space is also not aligned with the axis, meaning because the area is changing, there is a certain slant height. That certain slant height, so pressure will act normal to the slant height. Now because of that slight slope, let me try to redraw it from fresh, and perhaps it will be clearer. Because the area is increasing like this, the undisturbed area would have gone like this. So this is that small angle. So now the the pressure also acts on this area, and that angle it makes, let me call it alpha. So this angle alpha will be the same. So pressure is actually having a small component in this direction also. Okay, so imagine, if you imagine a cone like this, I've exaggerated the diagram. So the pressure is acting like this, but that pressure will have a component in this direction also, and this component can sort of cancel out, because over here this will be the component, but this component is additive. So there will be an additional force because of the slant nature of the peripheral area. So it will be due to the normal face plus force due to pressure on the periphery. So what is force due to the weight? It will be equal to, so rho times G times the volume. So now volume is equal to ds, which is the length of the segment, times the average area. So the average area will be A plus del A del S ds upon 2. So this is like the average area, but this points in the minus Ez direction. Okay, but we are writing the momentum equation in the S direction. So because this is the weight of the fluid, this angle is theta, meaning this angle is theta. So whatever this weight times sine theta is in the minus Es direction. So this entire thing will be minus sine theta. Remember that we are writing down the momentum equation in the Es direction. These are the fluxes which carry momentum in the Es direction. This is the force due to its weight in the Es direction. Okay, so we've found out one term. Let us, so what is the force due to pressure in the normal faces? So on the left face it will be P times dA on the left face. It will be equal to integral P dA on the left face, and this is simply going to be equal to P times A. On the right face it will be minus P plus del P del S ds dA on the right face, and this will be equal to P plus del P del S ds on the right face times the area. So this is the force, but it will act opposite to S. It is acting, that force due to pressure is acting in this direction. Alright. So these two terms are also fine. Apart from this, we want to find out the force on the slant face. Let me just, instead of drawing it inclined, let me just draw it flat. Alright. So the force acting on this, which has a component in this direction, will be this area. Okay, if I project it, so it will be the let me exaggerate the diagram a little bit more. Let me just draw the 2D. Okay, so the force acting on this particular face, the force acting on this particular face, which will have a component in this direction, will be the projection of this area, will be the force acting on the projection of this area. So it will be the pressure at that point times the projected area, right? So what is the projected area going to be? So we can sort of write this down as the pressure at a point. So let us say that this point is at a distance of s tilde. Okay, so at a distance s tilde, so p at s tilde times area of the projected area at s tilde. So this integrated over the entire length. So let us see what this is going to be. So p at s tilde will be p plus del p del s times s tilde. So when s tilde is 0, pressure becomes equal to p. This times the projected area. So the projected area will be the area at this cross section minus the area at the earlier cross section. Okay, it will be area at s prime plus some delta s prime minus the area at s prime. So essentially it is the dA, and dA will be del A del S prime times ds prime. Okay, so this delta will be ds prime. Okay, so convince yourself this is true. The projected area will be this cross section area minus the cross section area of the left, and using Taylor series you can easily show that it will be del A del S prime ds prime. Thus the expression, it becomes integral p plus del p del s s prime times del A del S prime ds prime, where s prime you have to integrate from 0 all the way to the end of the tube, which is located at a distance of ds. Okay, so s prime is just a dummy variable, okay, nothing else. So this becomes, so what is this, p del A del S prime, okay, this is as good as del S prime, no problem. So p del A del S prime ds prime plus del p del S prime del A del S prime s prime ds prime, and this becomes p del A del S prime. So ds prime, this simply will be equal to ds. So integral of this, okay. So integral ds prime is simply going from 0 to delta s. It's going from 0 to ds. No problem. This plus, what about this term? This will be del p del s prime del A del S prime times s prime ds prime. So s square upon 2. So this will be ds square upon 2. All right. So I can write down the force as p plus del p del s prime ds upon 2 times del A del S prime ds. And look, this, when we're writing it down using the Taylor series, del p del S prime and all these terms are actually evaluated at this term, at this point, and ds prime and ds are the same because it's simply the same coordinate system. All right, there is no offset or scaling of the coordinate system. So the force becomes p plus del p del s ds upon 2 times del A del S times ds. So this is the rigorous derivation of the force acting on the slant face. So then finally let's combine all the terms together. So this is rho u plus del u del s ds times area minus rho u square area. This is equal to minus rho g sin theta a plus del A del S ds upon 2 times ds plus pa minus p plus del p del S ds times a plus del A del S ds plus this term p plus del p del S ds upon 2 times del A del S ds. Let us simplify this. So on the left hand side, what do we have? So we have rho. So this u square a will cancel out. This will be rho u del s times a times ds. So let me. So on the left hand side we have this. On the right hand side, so this pa and this pa will cancel out. So we will have. So I'm writing down these terms. So that will be minus p del a del s ds minus del p del s ds times a minus del p del s del A del s ds square. Now let me write down this term. Recall that this is ds, this is theta. So ds sin theta is going to be dz. So this is going to be minus rho g a dz minus rho g del A del s ds upon 2 dz. let me write it down separately. No problem. This will be minus rho g del A del S ds upon 2 times dz. And let me write this term down. So it will be p del A del S ds upon 2 p del A del S, not this ds won't be upon 2, yeah, plus del p del S ds upon 2 del A del S. So del A del S del p del S ds upon 2 square, because it's 2 ds. Now in the limit, as delta s goes to 0, alright, the terms involving delta s square and delta s delta z, they will all vanish. So this term will vanish as compared to the other terms which contain only ds. So these terms will go to 0 faster than these terms, and hence they will be 0 prior to this term becoming 0. So it's basically taking a limit, nothing else. So if we take this, we have obtain rho u del s ds times area is equal to minus del p del s ds times area minus p del a del s ds minus rho g a dz. Okay, so these are the different terms. Have we? And the last term is this particular term. So plus p del a del s ds. So this term is this term, this term is this term, this term is this term, and this term is this term. Alright, so let's proceed. So this cancels out. On the right hand side, we have minus del p del s dsa minus rho g a dz. So on the left hand side, we have rho del u del s ds times a. So let us divide everything by a. So a cancels out. In fact, let us divide everything by rho also. And let us integrate it over s. So this integration from point 1 to point 2, from point 1 to point 2, from point 1 to point 2. So this will be u square upon 2. This will be minus 1 upon rho. So the u square upon 2 going from 1 to 2. This will be p2 minus p1. This will be gz2 minus z1. And that completes the proof that u square upon 2 plus p2 by rho plus gz up. There was a rho already over here. There is no more rho. Okay, there was a row already and I cancelled it. So maybe I cancelled it twice. And besides, the whole equation has to be dimensionally correct. So plus gz equal to 0. So we obtain the Bernoulli equation in this form. And of course, all the assumptions are true that it's an inviscid flow because we have assumed that the velocity is constant across a given cross section. It's a steady flow. And all this, I mean, it's a very restrictive form of the Bernoulli equation as we will study soon. But for this particular problem, we should appreciate that with the help of the momentum equation, we are able to obtain the Bernoulli equation. And strictly speaking, the Bernoulli equation is a statement of the conservation of energy, mechanical energy. And we all know that a momentum equation can be used to give us the equation for the conservation of energy. You know this from classical mechanics also. Let us consider a problem that of a rocket. So a rocket is moving with a velocity in the z direction, and it is given that the exhaust discharge speed is equal to V. So the exhaust discharge speed is going to be sort of in the frame of the rocket. This exhaust velocity is always going to be in the frame of the rocket. The exhaust gas density is rho E and the area of the nozzle is A. Alright. So we are asked to find out that if the mass of the rocket is m, and obviously the mass of the rocket changes over time because of the lost fuel, we want to find out the differential equation for the vertical motion. Okay, we want to simply find out the differential equation for the vertical motion, and let us say this is the ground. So we will consider this to be a control volume. We will consider this to be a control volume, and the control volume now has a uniform velocity, say b, in the z direction. So the control volume has now a velocity, but the control volume is not deforming. So let us write down the statement of the conservation of mass. So we will have ddt of m times now the momentum of the entire object. So we are writing the conservation of mass. So dm dt, this plus integral rho u minus b dot n dA equal to 0. Now b over here is the velocity in the z direction. So b vector is equal to b ez, while the velocity at the control surface, this particular control surface, relative to the velocity. So this exhaust velocity is actually equal to u minus b, right? So okay, let us write down the velocity of exhaust relative to the rocket is equal to the velocity of exhaust minus velocity of rocket. So velocity of exhaust with respect to the rocket is equal to VE in our, so this is going to be VE absolute. So this is VE absolute minus B vector. So V exhaust absolute is going to be velocity of exhaust with respect to the uh, rocket plus the velocity of the control volume. So VE is going to be actually minus VE in the Z direction, and B is going to be B in the EZ direction. So this is the absolute velocity of the jet which is coming out. Okay. So the velocity with respect to the rocket, right, is equal to the velocity of exit that is given. So this is simply the velocity of the exhaust with respect to the rocket. So this becomes dm dt. So look, m is now changing. We cannot make this 0. Despite the control volume not changing, the density itself inside is changing. This will be plus. So now velocity of whatever the exit velocity is here, the normal vector is also like this. So that sign will become positive. Alright. So this will become VE times AE times rho E equal to 0. So rho E VE AE. Alright. So this is quite important to know that the exit velocity is given with respect to the rocket. Okay, this is given. But for the momentum equation, we'll actually need the exit velocity absolute in the frame that we are observing the rocket. Okay, so for at the moment we have the conservation of mass as this. Let us write down the conservation of momentum. So ddt of m times. So now what is the momentum of the control volume? The control volume is now itself moving with a velocity equal to b. So ddt of mb, all right, plus the fluxes of momentum. So what are the fluxes of the momentum? So let us write down rho times u minus b dot n b. Okay. So this is the rate of change of momentum of the rocket. This is the flux of momentum, and this is equal to the forces. So the forces will be simple. What are the forces on the control volume? It is the mass times the gravity in the minus z direction plus some drag force. Let us call it FD. There will be some drag force acting on the rocket. Just let us put it as a generic force. So these are all we want it to be in the z direction, so we cannot write u as a vector. I mean, we are writing down the conservation of momentum in the z direction, so this will be u in the z direction. So what do we have? ddt of mb plus. So now look, this is where the absolute velocity is required. So uz is the momentum as seen from our frame of reference. So it will be rho. Now this velocity will be equal to b minus the exit velocity. So this velocity in the absolute frame is equal to b minus exit velocity Ez. So this is b minus b. So now u minus b dot n is again going to be the same. It is u minus b, this velocity, the relative velocity of the exhaust with respect to the rocket dot n, and that is going to be positive. So this is going to be simply VE times AE. So this is the rate of change of momentum of the control volume. This is the flux coming out from the control volume, and this is equal to the weight of the rocket plus an additional drag force. And look, the drag force is not actually in the positive direction, but we've just written down as if there's some force Fd. But in reality, Fd will act in the minus z direction, so you could have taken a minus sign over here as well. No problem. So what do we have? If we combine dm dt expression from this, so this is dm dt times b plus m db dt. So this first term is this, and essentially dm dt is minus of this. So this becomes m db dt minus b rho e ve a. So this first term is equal to this. Second term can be simplified to rho b ve ae minus rho ve square ae. So the left hand side, this term rho, yeah, this is rho e. So this term and this term they cancel out. So on the left hand side we have m db dt minus rho e ve square ae. This is equal to minus mg plus fd. So this is the governing equation for the rocket, and typically fd will be linearly proportional to the velocity, right? FD will be sort of related to the velocity, and so from this also we can write down. See, B is what basically. So let us call this a Z rocket. So B is essentially dz rocket dt. So we can essentially find out an equation for the location of the rocket. Okay, the important point is to understand how the relative fluxes come into picture. If you get this incorrectly, you will end up with the incorrect answer. It is important to understand all the relative velocities, all the fluxes, and the absolute. So the momentum will actually have the absolute flux, but with the relative the momentum will have the absolute momentum, but with the relative flux. Okay, if this momentum is not able to cut the flux, then their contribution will be zero. So that is that. We have looked at a problem in which we have derived Bernoulli equation by considering the sort of uh, flow along a streamline. Okay, so we found out the Bernoulli equation by integrating the momentum equation along a streamline between two streamlines. I mean between a across a stream tube essentially. Okay. So with this we end this particular session, and I'll see you next time. Bye.